Okay, kids, here we go. We're going to talk today about total internal reflection. Total internal reflection, which is an Italian word, Italian for reflection. Now I'm going to refer to this as T-I-R. From here on out, all the cool kids say that, T-I-R. Whoa, what you got going on there? I got some T-I-R. Whoa, dude. There's a T-I-R. Total internal reflection. Now, the thing is about what this is, it's a reflection, but it happens because of refraction. That's confuzzling. Yeah, it happens because of refraction, but we got a reflection. I don't get what you mean. Okay, so I'm here. That's why I'm here. All right, here we go. So, total internal reflection. Let's say we got this going on. You're under some water. You're at the bottom of a swimming pool. Hopefully not for too long, okay? And you can hold your breath. And let's say, I'll take this out of here, that you shine a flashlight. So here's you. You're holding a flashlight. And I'll make it angle it like that. Hold the flashlight underwater. Happens all the time. You do this at home, right? All the time. Yeah. Take a flashlight underwater and shine it. It works, trust me. So you take your flashlight, it's an underwater flashlight, people, an underwater flashlight, and you shine it, and it goes beam, bzz, tunk, and the beam goes up, gets to the surface. Okay, let's draw a normal. Okay, draw a normal. Well, why'd you do that? Why'd you do that? Because we're going to have some angles and some refraction. But you said total internal reflection. Billy, relax, okay? Relax. We'll get into it. So now we all know what happens when light is going from a more dense water to less dense air medium. We know what it does in relation to the normal, right? We all know. It moves. Billy, how does it? Away. That's very good, Billy, very good. Yes, it does. It moves away from the normal when we go from more dense water to less dense air. It's going to move away from the normal. So let's draw that in. Let's see, maybe it refracts away from the normal. Maybe something like that. Okay, so this would be our angle of incidence, and this would be our angle of refraction. Okay, we have a larger angle of refraction as we bend it away from the normal. All right, now let's say you're under that water and you say, I'm going to try to move over here. I'll move over this way. And so you get a larger angle of incidence. So you move the flashlight over here. So now maybe your flashlight is here, and you shine the beam, and the beam strikes the surface, and once again bends away from the normal. But now, since you had a larger angle of incidence, we should have a larger angle of refraction. We all know Snell's law, and that's what it tells us. Yes, it does. Yes, it does. So this is going to get a little weird. You don't know which line goes with what, so I'll put some numbers. This is line 1, and that was line 1. This is line 2. This is line 2. All right, so let's keep going. Let's keep going. Now, what would happen if I move the light a little bit wider here, a little bit wider, getting a larger angle of incidence? Maybe some of you can see what's going to happen. Maybe you can, maybe you can't. Okay, all right. So now if I have a larger angle of incidence, I can have an angle of incidence that allows an angle of refraction, because remember it's going to bend away from the normal. That angle of refraction allows that refracted line to ride right along the boundary. So this is I'm going to move this 2 here, I'll move that 2 to here. And here's line 3. And then line 3 gets a refracted angle that rides right along the boundary. That gives me an angle of refraction of 90 degrees. So now we're getting somewhere. All right, wait a minute. Uno más, muchachos grande. So let's move out the beam a little bit farther. So now we're coming in at an angle, the very big angle of incidence. Now what happens? Oh, go back to that name. Remember, we started the video, total internal reflection. Reflection. What happens is, if I get a large enough angle of incidence when I'm going from more dense to less dense, I can actually get the light to reflect back in the material. So line 3 shows that we get a 90-degree incidence or a 90-degree angle of refraction. But if I go to line 4 here, larger than line 3 with my angle of incidence, larger than that, I get a reflection off the surface, boing, and I get that. AP loves this. I'm not really sure why. I mean, I get it. It's kind of cool. It's kind of cool. It's actually like how fiber optics work, and I'll show you a little demo in just a second. But AP really loves this. It seems to me disproportionately, but they do. So you might say, all right, okay, well, okay, now what? Is that it? Are we done? Are we done? Silly rabbit. Tricks are for kids. No, Mrs. Physics, we need math. You know that. So this angle right here, I'm going to switch to orange. This angle right here, this angle that goes to line 3, that angle of incidence caused a 90-degree, so I'll put a 90-degree in orange up here, refracted angle. That angle is special, special. Just like some of you at home. You're special. Special, all right. Now, so that actually has a name to it. The angle, so let's write this down. The angle, you kids can all see this at home. Yeah, I'm looking. Yeah, you can. I'm using markers that aren't always black and blue, okay? Because that always looks like a bruise. They're black and blue marker. Looks like a bruise. Black and blue. I don't need you. I get this. Yeah, so I'm using some sweet colored markers here. Got orange. The angle of incidence that causes, are we still in view here? Yeah. That causes an angle of refraction to be 90 degrees, okay? So here's what we got. The angle of incidence, that's the orange line right here, the angle of incidence, that causes the angle of refraction, that would be the one that's riding along the boundary. So line 3, okay, orange and orange, to be 90 degrees, which our angle of refraction is 90, is known as the critical angle. That's known as the critical angle. Critical angle is the angle of incidence, which causes an angle of refraction to be 90 degrees. All right, okay, all right, okay. Now, let's do some math. Let's see how could we calculate this? Is there a way to calculate this? Could I calculate an angle of refraction of 90? Could I figure out what that angle could be? Yes. The German guy, the guy who has a good nose. Snell's law. Snell's law. Snell's law, let's get you over here. Okay, pulling you over. Okay, you're not getting seasick on me, are you? Okay, good. Low motion sickness. So Snell's law says Ni, sine angle I, equals Nr, sine angle R. Okay, all right, you use that. Yeah, we're good with that, right? Okay, so let's see. This angle here, the angle of incidence, which causes an angle of refraction to be 90, so my angle of incidence that causes an angle of refraction to be 90 is known as the critical angle. So what I'm going to do is, that's my index of refraction. I was pointing to the wrong one, the sign here. The sign of the angle of incidence, if it's critical, we change the I to a C. So the angle of incidence is called the critical angle under these circumstances. So I took the I out and put a C in there. Put a C in there. I took the I out. It's funny. Okay, so now, if I want to figure out what this is, I'll have to take the sine of angle critical and sine R, sine angle R, or sine NR, sine angle R, and divide it by NI. Okay, so that's my setup. Now here's the thing. Usually, not always, we're talking about refracting from something like water or plastic or glass into air. Okay, 9.82 times out of 10. I've done the math. That is correct. This will be air. So the vast majority of times, not always, so we've got to be careful of this, but the vast majority of times, the angle, the material up here, the index of refraction of this material is air. So the index of refraction of air, we all know, is 1. So that means this, NR, that's the index of refraction of the refracting material, is a 1. So that goes away. Usually it does. And for us, basically, it will. It will. Trust me. Now, here's another thing. The sine of angle R. Angle R is 90 degrees. What's the sine of 90 degrees? We all know that. Yes, we do. Deep down inside, dig it out. You know the sine of 90 is 1. Look what we got. We got ourselves a little equation here. So this is called the critical angle equation, derived from Snell's law, derived from a little bit of what's going on here in the picture, and then we end up with our critical angle equation. You take 1 and you divide it by the sine of the index of refraction. I keep saying sine for index today. The index of refraction of the incident material, which in this case, in my example, would be water. So if we were to calculate the critical angle for water, then it would be equal to 1 over 1.33. What's the sine of the critical angle? So 1 divided by 1.33, because that's the index of refraction of water. And we can do that. You kids are relatively intelligent people. You can do this. Yes, you can. Take 1 and divide it by 1.33, and you get 0.75. Okay, about 0.75. So this is the sine. The sine of this critical angle for water, the sine of the critical angle for water to air, is going to be 0.75. And so now, inverse sine that. So second function, sine, second function. Answer, 48.8. So the critical angle, theta C, for water, is 48.8 degrees. So what does that mean? That means if you have light that is coming up to the surface, here's my I dropped down this normal, so measured from the normal of 50 degrees, what would happen to it? So I have an I of 50 degrees in the water, boom, boom, going to reflect. Okay, it'll reflect, you get TIR. Okay, you'll get that reflection. If I have the angle of incidence at 48.8, it'll ride along the surface, and if I have an angle of incidence of, let's say, at 38, so maybe where it is here for line 2, it would refract out and still go out into the air. All right, now, this phenomenon is actually used in what's called fiber optics. I don't know if you've ever heard that word, fiber optic cables. But here I have my representation of a fiber optic cable. Okay, it's plastic, and it kind of goes down here, and it winds around. I actually got this off of the prop set for The Wizard of Oz. Back when I was in high school, when they made The Wizard of Oz in 1939, yeah, I was hanging around Hollywood that day, and they were filming, and they got done, and they had all this extra stuff, and it was a prop that was used by the Munchkins in Munchkinland. Yeah, you remember, we represent a lollipop guild, a lollipop guild, a lollipop guild, we... Wait, oh, wait. I don't need you, kids, I don't need you. It's true, I wouldn't make this up. I wouldn't lie to you. I wouldn't lie to you, besides I'm not lying, I'm standing. Okay, so now, we're gonna shut the light. Oh, actually, I've got a laser here. Okay, this laser, it's actually kind of old. We've had this laser now for 15, 20 years. Yeah, about 20 years. Big high power laser, show you it works. See if you can see that on. See, it works. It works. Oh, you're like a cat. Yes, you are. You were following that line. Yes, you are. I saw that. Yeah, you're a cat. Yeah, you are. Deep down inside. And so, this is a high-powered baby. I got to be careful with this. You got to be careful. It's like, oh, oh, ah, yeah, oh, 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 that is wicked hot. Wicked hot. Whew. I'm kidding. I'm a kidder. I'm a kidder. Okay. Like if you ever see one of these and you run, okay? Have you ever seen the Terminator? Okay, one of those on you Terminator, you've seen it? Run. Run like the wind. Oh, where am I? Okay, so I want to show you a little bit of how fiber optics works. So let's imagine this is our fiber optic cable. This is a piece of relatively cheap plastic. And I've got my beam. I got to shut the lights off. And I hope this works. I hope we can see this. Shut the lights off. Okay. It's a little dark. Hello! We're going to take this. I'm going to put the beam in the... Oh, get my hand out of the way there. Get my hand out of the way. And we get bouncy, bouncy, bounce, bounce. You see that? Bouncy, bounce. I have an angle of incidence where the laser is coming in. It's a very large angle of incidence. If we were to draw a normal, boom, 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 down there, and I get this reflecting pattern down the line. So actually, it's kind of weird to think about it. We have light that's reflecting internally in a clear material. So this is light that can't get out of the clear material. It's kind of weird. It's clear. It should go right through it. Well, it's bouncing down. It's going to be the total internal reflection. Some of it does make it down to the end, and it's kind of nifty and cool, and you get it coming out that side. You probably can't get the effect that I can see here. It's like if I'm looking at that end, it's really weird. It's kind of funky. It's bizarre. It's like all these little things going, makes your eyes hurt after a while. Yeah, probably shouldn't stare at laser light. So yeah, it's coming out that end, but it does do this total internal reflection thing. And so it's kind of neat. All right, so there we go. That is total internal reflection. And here's my laser. I used to teach you what laser is and what it stands for, light amplitude stimulated emission of radiation, and how a laser works, but that was just for fun facts, and now AP doesn't care anymore. So I'm not. You want to know how a laser works? Look it up. Look it up. You can do it. You can do it. Back in my day, we had to go uphill to the library to find that out. Of course, back then, I was barefoot, snowstorm, uphill both ways. Sometimes I was pregnant. It was rough. It was rough, let me tell you. You kids got it easy now. You can just Google it. Okay, so let's see. Total internal reflection. We went through how it works. Oh, you can still see it. We went through a math problem with it. I would expect you to be able to do math with this. There are several problems on the homework set that we have for TIR, total internal reflection. Yeah, we should be able to figure out the critical angle, or if given the critical angle, if you were given this critical angle, then you could figure out what the index of the material is. So the index of refraction of the material, you can do that as well. All right, I think that makes like a gift. We'll wrap this video up and see you soon.